Okay, good morning. How are you? So I'm just going to make sure that everybody is connected. And so a couple of things for today's lecture. First of all, today we are not going to have an exercise because, once in a while I give exercises when there is material that I would like to have you go through. Sometimes we're not going to have exercises. That, of course, is not going to change the way we will do the grading, as you can imagine, because I said in the beginning of this class that sometimes we're going to have exercise, some other times we may not. There will be fewer times those that we will not have an exercise, obviously, from those that we do. And then of course at the end, when I look at the points that we accumulate, that will be not on what I projected we will do in the class, but on the actual activity. So that's this. The other thing we're going to do today, and I wanted to spend a few minutes at the end of the class, is that now that I have put you in groups, so two things about groups. There were a lot of rearrangements that I had to go through. And also because some of the groups, the initial groups were depleted by moving people left and right, I moved, instead of leaving one group empty and confusing me, I moved all of the other groups by one number. So you may want to now revisit your groups, make sure that you know who are your group members, because obviously on the basis of your request, there has been some considerable rearrangement, I would say. And so there were people who in the past were telling me, I want to move from group A to group 9. Please don't use those numbers. You want to tell me with whom you want to be in the same group. Because I got those before. I made the rearrangements, but now that I have made all of them, I'm not sure your number 8 before reflects number 8 today. So send me those who want to make changes, and I hope they're not going to be too many. Just send me an email and say, I want to be with so-and-so in the group. That it's better for me to be able to make that change. So that is number one. Number two, in your section, because there are also honor students, I put all of the honor students into two groups. And then the other students in the different groups, because obviously for the honor students, some of them, not in the initially, but after the first midterm, I would give them maybe some additional work for the team homework. And so I wanted to have them separately. The last thing that we, as I said, we will do today is that I created, and this is for the first time, breakout rooms. And what I would like you to do is on the basis, just don't go wherever you want to go. I mean, I allowed you to select a breakout room, but I would suggest the following. Those who are on in 501, not an honor student in this section, go and join the breakout room that has the same number with your group. Say, if your group is number 3, 501, number 3, go to group, to breakout. I will tell you when, not now. Maybe now you can do it, in fact, even. I think I have not done this before, obviously. So my hope is in the breakout rooms, you can still hear the lecture, but you can talk with each other. If you don't want to do it right now, maybe not at this point, maybe the best thing in retrospect is to do it only towards the end of the class. So if there are any issues, then we work them out then. But what I was going to do is that it will be good, especially to have those breakout rooms so you have an opportunity to speak with your team members. Because I don't care if you work with your team members to even do exercises, to respond to my questions or other things that we do in class. But it's going to be good to be able to start to get to know each other. And so I will be doing that every time. I will create group rooms, breakout rooms for you. So for the 501 students from 1 to 17, go to breakout rooms now or when I tell you. You can go in and out if you wish, as long as you can hear my lecture and see what I'm saying. From 1 to 17. And then the 2 teams that I have for the honor students, please go room 1 for the honor students, which is 201. I mean, excuse me, group 1 for the honor students, which is 200-1. Please go to room 18 when you need to go, when you want to go. And for the second group, 200-2, is going to always be room 19. So the 501 students from 1 to 17 and the honor students 18 and 19. Do you have any questions with respect to that? Any questions?
Professor, when we do join join the breakout rooms, it disconnects us from the lecture and just brings
Okay,
us
then
like
don't, thank you for telling me. Thank you. So don't do this now. We'll do it in the last 5 minutes, or you will go to breakout rooms when I ask you a question. How about that? Because sometimes I will ask you a question now that we have been in teams during the class. I will give you like 10 minutes or 5 minutes to think about it. You can go to the breakout room, you can talk a little bit about that, and then you can come back. How about this? Thank you for telling me, because I have to tell you, I've never had that experience on Zoom myself, and I don't know. And Zoom is a very good medium for online, but you know, it's like it was never designed to replace the regular lecture. So we'll do the best we can. But thank you for telling me. There is another thing that I would like to suggest. We all suffer from the same problems with online. So for example, you as I do, don't it's like we talk to a black screen with a few pictures there. What I would suggest that you do, because it's good for me to know who you are, and then there are a few students who connect with me during office hours and I can see them, but the majority of the students do not do that. So what I would like to suggest is that when you speak with me, please turn on your camera, especially if you are to ask a question as opposed to say hi or whatever. Even with hi, I would like to see you. Turn on your camera and then you can turn it off again. But it will be nice, you know, for me to feel that I talk with a person as opposed to nothing that I see right now. It just, I think it's going to be good. So that as a suggestion. Okay, so any questions or any comments so far with the things that I covered about this class? Okay, since I don't hear anything, I gave you yesterday, I released 2 types of homework, and you will see that, as I promised, that it's not going to be more work. Instead of giving you 2 problems in individual homework, I will give you 1 problem in the individual homework, 1 problem in the team homework. The problems in the team homework will be more conceptual. And why do I do that? So this is going to give you an opportunity to talk and understand the concepts more. It's not meant, teamwork is not meant so far to do what you could do individually better, meaning sit down and write equations. But it's going to allow you to talk about the concepts and what you see, what you think, the definitions we are using, the meanings of the equations, and so forth. So I gave you 2 separate problems. For the individual, you will submit the work the way you normally do. For the team homework, I would like to have only one submission per team. I have, I believe there is a lead in each of your teams, but this is just for me that it was done randomly since I do not know the people specifically. It's up to you to change the lead if you want, or if formally or informally, and just have one person to submit. When you are in the same team and one person submits, the submission goes to all other people. And when I grade that paper, the grade goes to all other students. All right, so you know, it's done automatically. So that's what I wanted to say as well. And that's what I had to cover for my end. So today we're going to start with our lecture, which I have online for you. But obviously, since I cover additional things during the lecture, depending on how far we go in the material, then let me share this. And let me know whether you see what I have in front of me. Everybody sees that?
Yes, ma'am.
Okay,
Yes.
thank you. Yes. Thank you. What I would like to do today is, and I would like to emphasize this, two things. I know that, first of all, I have gone through your survey twice. I did it very early when you submitted it, and then as I was rearranging the teams over the weekend, I went through the survey again for a little more attention to some of the particulars. And I know that I understand that most of you think that this class is very conceptual, and therefore, because some of the topics are kind of abstract because we don't feel them, we don't see them, that a lot of you have come to this class with a lot of anxiety about what we are covering and how you're going to like the material. And I understand all of this because obviously I went through the same as a student, and then I have taught thousands of students since then, so I know exactly how it feels. The one thing that I have already said, I think, about the class, and I would like to repeat it, is this class has two problems, but they are not I mean, we see them as students as problems, but in reality, when you learn how to learn this material, then it's going to alleviate a lot of what we see as problems today. So there are two types of difficulties that people face. One is the concept itself, and the second is the math. And I understand both of those. So that's why we spent practically 2 weeks going over some material that you have seen at some point, maybe some time ago, and then we had to recall because this is important material to have in mind. A lot of this material has to do with geometry. And why is that? Because fields and antennas and circuits, now the fields, we don't see them, but the antennas and the circuits that create them are very physical structures. Like, it's not like a computer where you write a software, a code, and there is no physical structure into it. Circuits and antennas are physical, and for the designer, it is important to have a good visual understanding, to have the ability to see what he or she designs in 3 dimensions, to at least imagine it somehow. A lot of the designs is like art, as I said. There are guidelines for designs, but there is no, I mean, there is no package that does the design for you. The best designers who have the ability to visualize their concepts, these were the ones that made history in electronics. So what does that mean? That means that yes, math is important. Geometry, I would encourage you to revisit every time you see something you don't remember. Please take some time to go and revisit the material. It's important, not for this class alone, for you as an electronics engineer. Beyond that, I also know that in a class like that, when you start with math, then you go to physics, and then you try to make it through that mess in some ways, you lose the connection of why, of what we do with what matters. Even if the connection is there, somehow we are so engaged with the topic, then at the end you say, why am I bothering with this? I don't want to know what happens when a sphere, for example, with charges send something. Who cares about a sphere with charges? I will never design a sphere with charges to do anything. And so what I wanted to do today, and I will try to do in other classes, is to always start with a real application and tell you how this real application will benefit from the very specific thing that you see as unrealistic and idealistic, rather. And the reason we do that is because in electronics and in every field, to be able to attack a difficult problem, you need to reduce its complexity to something that you can solve. The best engineers and the best designers, circuit designers, are not going to rely on a parallel computer to check an idea. It's like any other designer in arts, or I will use one because when I was very young, I wanted to be a fashion designer. Now, I never happened, obviously, but there was a time when I was a teenager, before I got into becoming an electrical engineer, that I was thinking about that. Now, if you look at fashion design, people start drawing. You remember we talked about diversity, divergence, I'm sorry. We talked about divergence and how divergence is important in sketching, all right? Because you can really do something very simple, and then you get an idea of how it is, and then you try to materialize it. Artists and designers and fashion designers and other designers are using this. So they develop their own sketches. If you see a documentary that I saw about Yves Saint Laurent, he was an amazing artist who knew how to sketch. I mean, of course, in his own way, but before he would think about materials, before he would think about colors, before he would think about how to put this together, he would go on a piece of paper and sketch his idea and see how it is. And then from there, he would decide how to go about it. The same thing applies to electronic design. Designers work in the same way. You have to sketch an idea and then go and create it. Now, of course, an artist and an engineer have one fundamental difference. An artist can go and do something really crazy that may not be able to, may not be realistic. We cannot do that. We are constrained by the physical laws. And so how do we manage that? That when we have an idea, we try to simplify down to something that we can even solve without a parallel computer. Then you see whether your idea can be materialized, and then you start building on it. So we follow the same process like any other designer, but we are constrained in some way. And that's why we always try to bring very complex problems down to some very simplistic ones that we can solve even on a piece of paper, and then realize, this idea, can I make it really? Because if you have an idea that cannot be made, does not make sense physically, then you cannot continue. All right, so that's what I wanted to tell you. A lot of times we take very complex problems, we go down to something very simplistic, And the solution of that very simplistic problem is the key to whether you can make another more complex one a reality. So here I wanted to show you why it was important to find the electric field that is created by a charge. All right, so this is considered very fundamental. We start with one charge, then we put 2, 3 charges that were point charges, and we placed them in space, and then we went to an infinite line charge, all right, last time. So now I wanted to stop and say, why is that important? And I wanted to bring in front of you a very realistic circuit. So look at the printed circuit board. What that really is the printed circuit boards. The design of a printed circuit board is very intense. And it's created so you can place in there your microchips, your microprocessors, for example. You can place there your passive elements. You can place there your capacitors, your resistors, if it's not a full monolithic design. But in reality, you will see, because you have to connect, like take this one here, for example, that I wanted to show you. Look at this one. Right there, you're going to place a chip. And then, so you have to fit the chip. It has so many, ports from each side. And so you will have to run all of these lines, most of them digital for some applications. Some of them, if the chip is high frequency, it's going to be high frequency lines. But let's assume that we are totally digital here. So all of these lines have to run here, here, you see all of them. And that's a very simplistic chip. As a matter of fact, I'll show you another more complicated one. And then you have to run them. You have to do the layout, and the best layout wins the day, practically. So takes it all, as they say, because in all of the layouts have to be, so they don't create any parasitic effects, and are the smallest in size, and are the easiest to fabricate. So this is a circuit, a simple circuit board design, and this circuit board is for testing, where you put your different circuits. It's not even a realistic something that you put somewhere else. Do you want to see a real circuit board? This one. Look at what is happening here. This is from a real company. I mean, this is from a company. It's a real circuit board. This is where you put your chips in these areas. And this circuit board is multi-layered. Look at how many lines you have. The green lines are on one layer, the yellow lines are in a different layer, the red ones are in between. And the layouts here, like this yellow here, shows where you will place your chip on top. All right, so it's a multi-layer circuit board. So you have all of this, and look how the lines here do this. Let me see, this is too thick. Look how the lines here go like this, all right? Now, if you were to design all of these lines and then don't do it well, and that's another one, even simpler, but this is a detail. Again, here you have a chip. This is also from a testing circuit board. Here you have a chip that you place. These are the pins, as we call them, the inputs. You have so many pins. You have, each pin has to be fed by a line. Some of them have to go to ground. Some of them have to get digital signals. All right. So what is happening when your lines are too close? What is the biggest problem in printed circuit boards? I mean, in the late 90s, with one of my students, we were working on a Pentium 7 at the time to look at the noise on the package. And they call that the switching noise. There are different names. They call it impulse noise. They call it switching noise. Sometimes there is I delta noise. I mean, there are different types of functions on a chip that practically do the following. You have a line here that has that sends digital pulses, practically DC signals, and then these lines are this close. Even if these lines are too close, then what happens is that one line it creates an electric field that changes the electric field from one line, changes the electric field on the other line. And what do you do in DC? DC, when you change the field on the other line, practically you change the value of the pulses that go through, which are 0 and 1. And so where you are supposed to have a pulse 1 value, they change the impact of the near neighboring electric line due to its electric field that is generating, may bring it down to 0. And changing from 1 to 0 is like you send wrong information to your microprocessor. So what we are trying to do is we try to understand what is the fundamental impact. I mean, I cannot solve this problem like this in my head, the whole thing. There is nobody even to solve this problem. It's a very complex problem to solve in a computer. And people are not going to do that and go and spend, a week trying to do this before they decide how close or how far away the line should be. So what do? You take a problem like this and you try to split it into simpler problems. So for example, if I have these two lines, one here and one there, I would like to see how close I can bring them so I have a large impact on the other line from the electric field of one of them. And then so I start with the infinite here, the concept of the infinite line charge. And I see we solved that last time. We were able to find the electric field from that. And then I go from that to the finite line charge. And why do I do finite? Because look at this one here. There is this line that we have. Let me see. Right. There is this line that we have here. All right. And then there is the next line to it. And in fact, in some other cases, it's going to be even more. But this other line, it only comes close by this distance. So what these people are doing is the following in the design, which is kind of interesting. If I have a limited space, and if I want to bring these lines very close, I may bring them very close, but not for too long. Because if I bring them very close, but only for a short distance, then the impact is going to be less than the impact I would have if I bring them too close for a long distance. So you will see lines come together for a short time and then they go away. And then in fact, you see it even here more. So look at this one. Look at these lines. They came all together, but only for a short distance from here to here. From there, here, they brought them further apart. You see that? So it's all designed. Look at these ones. Look at these ones. Only for a short time, you bring them together and then you take them apart. So otherwise, you're going to have very high, very large problems with noise. And so this is from here, you find how long the line can be before it creates too much of an electric field on the other line. So we will do this together. And then also you start looking at electric field from a surface charge. Like if you have a big surface like this one, and there is charge on this surface, everything has a charge on a chip, on a printed circuit board. Everything is on a voltage. Even the ground has a voltage. Even if it's a ground for that, in relation to an absolute ground, it is at the voltage. So there are charges everywhere. So if you have this charge here distributed on this, what is going to do to the line next to it? You have so many big areas here which are at particular voltages. So then we're going to see at electric field from a surface charge. And then we will see what happens when we have field from a ring charge. And then we may go to a sphere, but this is mostly for antennas. So that's why we did these fundamental problems. We don't do this just as simple mathematical exercises. We do them because they're important, they're easy to solve on paper, they have simple equations, and they give you a very interesting, a very important rather sense of what is going on in your designs. So this is as an introduction, and I will try at least once a week as we start on a new type of problems to tell you why these problems are important. Okay. Now, the other thing that I wanted to tell you, and we will start with this, is that I want you to look beyond the math. I know that math can be problematic. And then if you have problems with math, you get stuck. But after we do the math, you need to understand what the math is telling you. The math is like, I was thinking, it's like you go to the Egyptian pyramids and you try to translate here hieroglyphics. Okay, so translating those is huge, is a huge problem. I mean, people are trying to find even the meaning of some symbols. But after you spend, say, months finding the meaning of the symbols, you don't stop there. You try then to understand what the whole sentence says. Because what's the point if you see that one bird means something? And then so you know that every time you see this bird, then it means something to you. Are you going to stop there? Of course not. You're going to go back and take this and try to understand what is the meaning you get. The same way we apply math here in electromagnetics. And for me, that I'm doing circuit design, for example, math is important for me to understand the physics. So I can take that, put it in my head, and then understand what I'm saying. Because if I am to be asked to solve this problem here, this one, I'm not going to put that in the computer. There is no computer enough who can do a simulation of this without going to a parallel computer and without waiting days to get the results. And sometimes the results will not even be correct. All right. So the layout is done like that, but an analysis of this, not. So in any case, that's what I want to tell you. You take from these fundamental problems, you develop what we call intuition. That intuition will tell you, in a good designer, you will see some lines too close and say, no, this is not good. You're not going to go and solve the problem in the computer to say these lines are too close. All right. That's how we do this. And so I know it's a different way of looking at what we do, but I have to tell you, a circuit designer is a higher form, practices a higher form of engineering, because you create something new. Circuit designers that have done new things have breaking ground for some new applications in Google, in Intel. You know, these are the top people who run, like, they start the new product lines because they created something that others have not been able to do. And that's the kind of the person you can be if you learn things the right way. Okay, that is my introduction. And I think it's important so we remember why we do that. We don't want to lose ourselves in the math and the physics and forget why all of this is important. Any questions about these things that I said? I may have taken a lot of time, but I think it was important to do it. Okay, now we know why I'm solving this problem. All right, I'm not doing it just twist your minds. I'm doing it because if I have one of these lines and one of these lines is here, assume that one of these lines, a section of that line that I want to bring very close to others, is this one. Is a section of a line that has a particular charge. And I simplified, obviously, the charge in real circuits. The charge does not stay uniform, has small variations. But in this particular case, I will consider it uniform. It's still going to give me a good hunch, of what I need to do. So I will assume that this line is from O, which is the center of the coordinate system, to A, has a length. And I will assume that this length is given. All right. And as a matter of fact, you will see that in this particular problem, instead of giving the length, we give in a different way the two angles, alpha sub A and alpha sub O, that you create here between the observation point and how far you are and what is your position in relation to this length. Now, these two angles are known because you know rho, which is the distance of P from P prime. All right, so this distance is known. You know the distance Z sub P, which is here. So practically, you know the distance O or OA. So you know the length of this. So practically that could be from here, there. This length could be L. All right, so with simple geometry, if you know L, if you know this a P, then you can find all of these angles here. And so practically you can transform these angles into all of these dimensions, if you like. And we will see later how to do that. So now I want to solve this problem. I want to see that if I select point P, and that can be on another, this point could have been on something like that, on another piece of line here. All right. And I wanted to see what the interaction is from the charge on line OA to my point P. And then, so how do we solve this? We start with Coulomb's law. Here, Coulomb's law says, oops, this one. Coulomb's law says here this, that the electric field that is created at point P because of the this charge OA is given by this formula. And what is this formula including? It includes, of course, the 4 pi epsilon naught, but then it includes this vector R from this vector here. And it has this form. I took it in this form because it's easier to write the vector. I will avoid having to identify separately the unit vector otherwise. So how do I, first of all, so the first thing I have to do there is to find R. How do I find R? From here, from this. And R has, I write it in the form of a coordinate system. It is on, I have selected point P to be on the x equals 0 plane. So in fact, I can write here that this is on an x equals 0 plane. Okay. And then the other thing that I do, I write Z there as a function of the angle A. You see A here? A is here. I have, and A is this one, as a matter of fact. A is this. Don't know what then. This. That's A. So I'm writing this in that form here. So since I have decided to specify the relationship between this point P and this charge here, the line charge, in terms of the angles alpha sub A and alpha sub O. So I will have to write everything as much as I can in terms of these angles. So of course I have an angle alpha, or A, I call it alpha rather, to differentiate, which is used to specify the position of P in relation to this small delta Z section of this line charge. I consider the delta Z section, and then I will integrate over the length of the charge. So then if you follow the steps, I write this one here, right? What I did, I went from the initial Cartesian coordinate systems to something that involves this angle. I did it in fact in cylindrical, if you see here. Okay, R, rho and alpha. And what is rho? Rho is this one, you see? Because I know where point P is if I find the line that goes perpendicular to Z, then I can define point P, and I use that rho because this is nothing else but the radius in a cylindrical coordinate system. So I found this. And then I went and I computed this one, which I needed because according to Coulomb's law, I have to calculate this in the denominator. All right, so the magnitude, I found it here, this one. And then from Z, I found also dz as a function of rho and a alpha. So the only unknown, what I have done so far, is to be alpha, this angle alpha. This is my only unknown. And then it's going to be easy to integrate and find the total effect, the total field from this line charge by integrating from dz from O to A. But instead of integrating along C, I will integrate with respect to angle from alpha naught to alpha sub A. And then, so I just do the math here. This is math I can do by hand. It looks complex, but look how it simplifies to this one. And then I do the integrations, which are also simple, very simple integrations at the end. And I find a very simple formula. If I do the integrations for each one of those, are integrals of sine and cosine, and then I write them in this form. Then what I find is the field in a form that I can understand. All right? I write it in a form that I can understand. It has, of course, the charge Q sub L, which is the line charge density. And it has the distance of my point, the vertical distance of my point from the Z axis. And it has the angles alpha sub naught and alpha sub A. And now these expressions are simple because I can see what are the impacts of, and I can even do a very simplistic plot that I can see what is the value of the total field from this a finite length line charge to my point P. So for example, I could ask you, say, in one application to say, okay, get this one and tell me what is, for example, so question here, it could be, what is the total magnitude of the field, or this one or that one? So what you do is that you take these two, if you wanted to find the total, and then you either do them in the form and you find it, and other you keep using the angles alpha naught and alpha sub A, or you eventually translate it into a length and a distance, however you want to find it. But these are expressions that you can use to calculate, for example, because that is what is going to be of interest to find here for this given finite length charge, which is like, you remember, this is the line charge, and this is a point. For example, let's assume that this point was on another line, all right? This is your one line, and this is another. And you want to see how close you want to put this line. So practically, you're looking at this row. So you can plot for a given length, all right, length L, you can plot a curve for this one. And this most probably is going to look like this, all right, with respect to rho. So practically, you can figure out from a simple graph like this, if say you want your magnitude of V squared to be less or equal, for example, to 1 microvolt, if you want to do this per meter, for example, all right? If that is what you have calculated as your limit, then you can plot it here, and then you can find out how small, what is the smallest value of rho that is going to give you this relationship. And that you can use easily. And then that's how you get the design rules. See, a designer for a new circuit also develops design rules for everybody else. Consider a fashion designer. The person makes one dress or one pair of pants or one jacket, and then develops rules on how everybody else is going to make 1,000 of them if they want to sell them. Or, for example, a artist like Da Vinci would develop an idea on how to make a hand, and then will teach all of his students on how to make hundreds of hands. Because if you see all of Da Vinci's paintings, remember we talked about the hands in the creation of Adam, in that famous painting? Well, you know how many similar hands? I mean, there is a study that I saw some time ago, how many similar hands they painted on all of the other. You don't pay attention because there are so many people in all of his paintings, but if you see their hands are very similar, because he decided on how to do a hand or a couple of them, and then he told all of his students who were doing most of the work on how to design those hands. He did only one, he did the original. And then he gave guidance, what we call design rules. But the initial design rules for him came out of other considerations. For us, they come out of this if it is about switching noise. So this is why those are important. So you don't think that you're wasting your time with things that are immaterial. So I would like at this point, what time is it? To make sure. It's 48. We have 2 minutes before. I will, next time, we're gonna continue a little faster, and what we are gonna do, and I will suggest at the end of Friday, to put all of these equations that we develop for these fundamental problems. I have listed them here. There are 5 fundamental problems we'll do in this class when it comes to electric field. And then we will develop a list of each of the problems with the final form of the solutions we found. So you will not re-derive them again, all right? We derive them once. But do you have any questions so far?
So you said the magnitude squared
could you turn on your, let me see.
Yeah, I would turn it on, but I worked out before class, so I don't have to show it on.
That's all right. Go ahead.
But did you say that the example question was, what is the total magnitude of the electric field for that the magnitude squared?
Yes.
Okay.
That is, in fact, what I, as a design, this is the most critical result of my exercise.
Okay.
Oops, let me see. Let me erase that and do it with red. This one. For a given L, which is the length of this charged line, and for a given distance from that row, this is the most important graph that I can get for design, because it shows me how close. And in fact, what I think now, in retrospect, I will do it for you next time, and then I may ask you to do one of those for one of our homeworks this week to show how the magnitude, it could be square or it could be just magnitude, all right? It does not matter. Usually square goes faster. Square shows power. That's why I like the square. It's not shows exactly the power, but it's proportional to it. So you can show how the electric field varies if you try to put any other conductor near this charged line. Any other questions?
Thank you.
You're welcome. Any other questions? So the next, I have to pay attention to this, because I will give you a problem like this for the homework. And I will ask you to plot the electric field like this, that I have it here. And we'll see some other also examples. We'll do it a lot more often moving forward to see how the electric fields vary, because that's important, all right? It's not just solving mathematical equations. Any other questions, comments? Okay, so we did not have time to get in the rooms today, but the exercise I will give you on Wednesday is going to be in class, and I will give you a particular exercise to do it in teams. Okay, so you can do it in breakout rooms. We'll do that. Any questions in general about the breakout rooms, about whatever?
Professor, I have a quick
Yes.
question.
Tell me.
I'm in the honors section.
Could you speak out a little louder, please?
Can you hear me now?
Yes. Yeah.
So I'm in the honors section, but my team is not an honors section team.
Oh, really?
Yeah.
Okay. What could you send me an email separately at Katehi, not through Canvas, but directly katehi@tamu.edu, and tell me so I can see your name and found you and place you in one of those?
Yeah, I can do that. Thank you.
Thank you. I don't know why I missed it, but thank you very much. Okay, well, we'll see you then on Wednesday. And we have office hours today for anybody who wants to join. Thank you.
Thank you.
Thank you.
Professor, I had a question.
Yes, go ahead.
So the angle A is just what we get from the geometry of the distance between the point that we're looking at and the line charge, right?
Yes.
Okay, we can
Yes.
just find out using like sines and cosines of the angles.
Yes.
Okay. And why
Right.
in the equation of the magnitude of r is it 1 over the cosine? Is that just from the geometry there?
It's because it goes like that. It goes as 1 over rho.
Okay, so that's indicative of like the electric field.
Yes, and that is here, you see?
Oh, I see. Okay.
See? And it goes like that.
Okay, thank you.
You're welcome.